the topic on spread footing, no? So this meeting we're going to discuss the second type of footing, and that is the rectangular footing. So I've already posted the copy of the lecture material in Canvas, so you can already download it now. So let me share to you my screen. Okay, can you see my screen now?
Yes, sir.
Okay, so our topic for this afternoon is the design of rectangular footings. So all things being equal, the square footing is the most economical, no? But there are situations where we cannot use the square footing, such as, for example, if a column is placed close to the property line, no? So that if we use a square footing, the footing area will go beyond the property line. Okay? So in this case, to maintain the footing area, no, while not going beyond the property line, the footing will be longer on one side and shorter on the other side. So what we will have is a rectangular footing, no? Now another situation is when, for example, two columns are placed relatively close to each other, so that if we use a square footing, the footing area for the two columns will overlap. No? Yun na ang situation. I hope you can see the drawing. So kini siya ang may tabo nga in order not to avoid overlapping of the footing areas. So instead of a square footing, no, so atong kuan will be rectangular footings. So natay gamayng i-maintain nga gamayng space between the two footings, no. So yung na the footing will now be longer on this side while shorter on this side. So what you will have is a rectangular footing. Okay. Now, for the second example, another possible solution will be to combine the footing for the footings, no, for the two columns. But using a combined footing will require additional reinforcement, no, the top reinforcement. So as much as possible, we try to avoid combined footings. Mas expensive siya, no? So let's move forward to the design calculation. Now the design of the rectangular footing will follow along the same or similar lines, no, as that for the square footing, with a slight difference, no, as we shall see. So in the problem, design a reinforced concrete footing to support a 600 mm square tiled column carrying a dead load of 1,800 kN and a live load of 1,800 kN. So the width of the footing is limited to 3 meters. Then assume the allowable soil pressure at service load to be 240 kilopascal. Use F sub C prime 21 and Fy 440. So again, in this case, no, there are certain preliminary data that we need to determine before we can design the footing, no, such as the size of the column. We need to know the load carried by the column, which is to be transmitted to the footing. Then we also need to know the allowable soil bearing capacity, and we have to determine the material strengths, no, both for concrete and for steel. Now in this problem, we have an additional constraint, no, that is the width of the footing is limited to 3 meters. That is on one side, as you can see in this figure, no. So this dimension here is not to exceed 3 meters. Probably there is an obstruction close to the column, or we have a property line, no, which is situated 1.5 meter from the column center line. So that will limit the width of the footing to only 3 meters. Okay, so we have the following steps. In step 1, we proportion the footing dimension based on service load condition. So we calculate the total column load as the sum of dead load and live load. Then we estimate the weight of the footing to be 10% of the column load. And the total load to be supported by the soil will be the sum of the column load plus the assumed weight of the footing. So next, we can compute the required footing area by dividing the total load supported by the soil by the allowable soil bearing capacity. So we get 16.5 square meters, no? Now, we try first square footing if that is possible. So we have the square root of the area gives us a required dimension of 4.06. However, this exceeds the width limit of only 3 meters. So we cannot use square footing here, no? So in that case, we try to verify whether the rectangular footing is okay. So the length of the footing is equal to the required area divided by the maximum width. No? So we get 5.5 and therefore we have 3 by 5.5 meter footing. No? So after this calculation, we already have the footing dimension. So the next step will be to calculate the factored column load. We multiply the dead load and live load by the corresponding load factors. Again, the 1.4 and 1.7 load factors is based on the older code. The recent one requires only 1.2 dead load plus 1.6 live load, no? Which is the one that you are going to use in your plates. Then the net upward pressure. So we divide the factored column load by the actual area of the footing. So we get 338.2 kilopascal. So after this, we can now proceed to design the footing slab, no? So the next step will be to calculate the depth required for beam shear, and next will be depth required for punching shear. Okay, now for the rectangular footing, there are two possible critical section for wide beam shear failure, no? So we have the wide beam shear failure across the short dimension located at a distance d from the face of the column. Nasya diha, no? Try to highlight that one. Okay, that is your critical section for wide beam shear in the short or parallel to the short side. Then we also have a wide beam shear, possible wide beam shear failure parallel to the long side. Okay. Now between these two possible nga failure plane, the failure plane in the short or parallel to the short side is more critical, no? Because you have a narrower width and therefore a smaller resisting area, no? So since we are already sure that the short side will govern, then we don't have to check for wide beam shear across the long side. Okay? So we have only this one here. So we calculate the shear force that will act at this critical section, which is simply the upward pressure multiplied by this tributary area, no? Which is the area outside the critical section for shear. So we have the calculation here in step 2A. Then shear capacity in step 2B. So for beam shear, we have P16 square root F sub C prime BD. So from step 2A and 2B, we have the shear force in terms of the effective depth. And in step 2B, we have the shear capacity in terms of the effective depth. For adequacy, so the shear force should be less than or equal to the shear capacity. And of course, the limiting condition is when they're equal, no? So we equate the two, then we will come up with an equation which can be solved for the value of D. So that's our effective depth for beam shear. Now next, for punching shear. So critical section for punching shear occurs at d/2 distance from the column face, no? So that occurs around the column perimeter. So if the column dimension is 0.6, then the dimension of the critical section will be 0.6 plus D, no? Since you have d/2 plus d/2 on each side. So the force that will act to shear the column or the footing, no, at this critical section can be computed in two ways, no? We can have using the free body diagram outside the critical section for shear, and then you will get the upward pressure multiplied by this tributary area, no? Which is the column, or rather the footing area minus the area within the critical section for shear. Or you can have if you consider the free body diagram inside the critical section, then you have the downward column load, no? PU, then minus the resultant upward pressure exerted by the soil, no? So resultant upward pressure is the net ultimate soil pressure multiplied by the area bounded by the critical section for shear. So you can do it both ways. So in this calculation, this is using the area outside. Okay. Now the shear capacity will be phi 1/3 square root f sub c prime BO times D, no? Where BO is the perimeter of the critical section. That is equal to 4 times the length of each side, no? So 4 times 0.6 plus D. So from step 3A, you have BU in terms of D. From step 3B, you have phi BC in terms of D. Then for adequacy, the shear force should not exceed the shear strength. And the limiting condition is when they are equal. So we equate the two. Then solve the resulting equation for the value of D. So based on wide beam shear requirement, you have 0.839. Based on punching requirement, you have 0.725. So the larger value governs, which is 0.839, but we rounded off to a more practical value of 0.85 or 850 millimeters. So after step 3, we now have the effective depth, no, of the footing, and effectively we have already computed also the thickness, no. So effective depth plus concrete cover below the bar, which is usually taken as 75 or sometimes 100 mm, and you will get the thickness of the footing. So after solving for the effective depth of the footing, then the next step will be to solve for the steel reinforcement. Now, unlike in the design of the square footing, no, where your steel reinforcement will be the same in both direction by symmetry, no, but for rectangular footing it will be different, no, in the long direction and in the short direction. So in step 4, we solve the long direction steel. So by long direction steel, we mean the steel bars which are placed parallel to the long side of the footing, no? So the critical section for bending will occur at the face of the column. So in the plan, you have here the critical section. In the section elevation, this is your critical section here. So that part of the footing which extends from the column face to the edge will behave more of a cantilever, no? As a cantilever, so acted upon by the upward pressure. So you have the resultant force, which is the net ultimate upward pressure multiplied by this tributary area. Then multiply that by the moment arm, no? Since this is uniform, then the resultant will be acting at the centroid of this tributary area. So that is at a distance of 2.45 divided by 2. Okay? So we have here the calculation for the bending moment. Then after we have the bending moment, the succeeding steps will be on reinforced concrete design. So which I would not elaborate anymore, no, but these are the steps for singly reinforced design for calculating the amount of steel. So we compute the moment resistance coefficient RU equal to MU over phi BD square. Compute the strength ratio M, which is Fy over 0.85 F sub C prime. Then compute the required steel ratio, no, using this formula. Rho equals 1 over M, quantity 1 minus the square root of 1 minus 2 RUM over Fy. So we have M, you have RU, you have Fy, so you can compute required rho to get an answer of 0.00395. Okay, this one we have to compare this with the minimum steel reinforcement ratio given by this formula, no? 0.25 square root F sub C prime over Fy, but not less than 1.4 over Fy. So between these two minimum, 0.00338 governs, no? And since row required is greater than row minimum, then of course we use row required. Okay. So row multiplied by BD, you get your steel reinforcement. So you have here the answer. Then after that, you select the bar diameter, 20 mm, 25 mm. No, this is an iterative procedure. No, so you select a bar diameter, then compute the number of bars based on the assumed bar diameter. So the required number is 20.6. We round off to 21. 25 mm diameter bars. Now the 21 pieces of 25 mm diameter bars will be distributed evenly across the short weave, no? So equaling yung spacing. So if you compute the spacing, we have this formula which I think you can easily follow, which we get 116 mm. So that is greater than 75 and less than 200. So that's okay. So that's it for ano. Now for the short direction steel, ano siya, no? By the way, feel free to interrupt if you have some questions. Now for the short direction steel, so that is the steel that will be used in order to counteract, no, bending at this critical section. Or critical section for moment will be at the face of the column, it's parallel to the long side. Okay? So natay bending dire, so ang steel will be placed perpendicular to the critical section for bending. Okay? So we follow similar calculation for determining the factored moment, that is the upward pressure multiplied by this area, then times the moment arm, which is 1.2/2. Then RU, row required, then compare with row minimum. Then now you notice that the required steel ratio here is very small. No, it is very much lower than row minimum. So the code allows us to use row less than row minimum, provided we supply 33% more. No, so we take 4/3. No, that is 33% more. 4/3 of row gives us 0.00129. So, and this one we have to check this against the absolute minimum, no, which is required to control temperature and shrinkage, which is for FY equal to 414, it is 0.0018 BT. For FY2 equal to 276 megapascal, you have 0.002 BT, no? So here we have 0.0018. Okay. So ang 0.0018 will govern. Now actually kini siyang value, no? This is the amount of steel reinforcement we need to supply to control thermal and shrinkage nga cracks, no? As the concrete will tend to dry up, it will lose moisture, then there will be tensile stresses develop in the concrete, no, especially if that shrinkage is not allowed to occur freely, no. But in the case of the footing, well, there is no restraint, no, at the edges of the footing. So in this case, the concrete will be free to contract, no. But anyhow, we just supply the minimum, please, no, the minimum amount to control thermal cracks. Now, kanisiyang 0.0018 should be multiplied by BT, no, rather than BD, because thermal reinforcement are to be multiplied by the gross area, no, rather than the effective area. I'll try to make a correction here, no. It's 0.0018 multiplied by B is 5.5 meters, then this should be T, no, instead of B. So, kanisiya, no? Kanisiya, ay temperature man may ni-govern, we multiply, that should be T instead of B. Now, unlike in the long direction steel, no, where the steel bars are distributed evenly, in the short direction steel, more bars will be placed at what we call the middle strip, and lesser bars will be placed at the outer strips. No, I think that is understandable because, of course, the larger pressure will occur near the column, no, other than at the outer or at the far edges, no. So mo nang mas kuanta mo consider kaning middle strip will be as wide as the short side, no. So if the short side is 3 meters, then we have 3-meter middle strip here. Then the remaining portion will be 1.25 meters each, no, for the outer strips. And how are we going to distribute this amount of reinforcement? So we distribute it according to this proportion, no? So the area to be supplied in middle strip will be 2 over beta plus 1 times the total area required in that direction, no? Where beta is what we call the aspect ratio. So that is the ratio of the long side to the short side of the footing, no? So 5.5 over 3 gives us 1.83. Substitute here. Then this is the portion of the area to be supplied in the middle strip. Now the remaining portion, which is the total area minus the area in the middle strip, divided by 2. And for each of the outer strip, we supply 1198. Now normally we choose the same bar diameter, no, in the short and long direction. That is for practical purposes, but that is not absolutely necessary, no. So as long as we are very clear in our details. So here, instead of using 25, no, I just assume 20 mm. That is the area of 20 mm diameter bar. So we can compute now the number of bars in the middle strip and the number of bars in each of the outer strips. Okay, we check the spacing. So only for the middle strip, because this is where the bars are more closely spaced. So we use similar formula. Then we get an answer of 146. So this is greater than 75 and less than 200, which are the desirable limits of the spacing. So okay. So that's how we design, no? So this is the one of the difference between the design of square footing, where we have the same number of bars both ways, but in the rectangular footing, it's not the same, no? And in the distribution of the bar for the short direction steel, you have more bars placed in the middle strip and somewhat lesser bars placed in the outer strips, no? Strips are located farther from the column. Now we check for development length. So if you look at the plan view, which is more critical as to development length, in the long direction steel, you have a longer embedment, no, for the rebar. But since these are different bar diameter, then we just compute in both directions, no. So I've already introduced to you the development length formulas. So the same formulas are applied here. And solve for dowels. So again, dowels are optional, no? So the common practice is just to embed all the column rebars into the footing. And if we do that, then we don't have to calculate dowel bars, no? But in purely actually loaded columns, no, that is not it's not absolutely required, no. Yeah, ang tanan gyud nga column rebar embed nimo, because what you need to do is simply to assure adequate load transfer from the column to the footing, no. And that is by bearing at the contact area. If that is insufficient, then you provide the dowel bars, no. It will act as compression bars to also help in transmitting the downward column load to the footing. Okay, so this is the calculation for the amount of dowels, then the development length for bars in compression. Step 6, we check the weight of the footing, because in step 1 we just assume this, but now we have the effective depth, no, of 850 plus a cover of 100 or maybe 75 if you like. So we get a total thickness of 950 mm. So the volume of the footing is length times width times thickness. And the weight, you just multiply that by the unit weight of concrete, no? So the actual weight of the footing is slightly higher than the assumed weight, no? So, but the difference is very small, so there is no need to revise the calculation, no? Will not significantly change, no, the final answers. So finally, no, we have here the detail. So again, what is important in the detail is that we convey all the necessary information we need so that those in the field will be able to construct the footing as we intended it to be constructed, no? So we show in the detail the plan dimension, so 5.5 by 3 meters. Then we show the column location in relation to the footing. Then we show the arrangement, no, of the steel reinforcement. Okay. Then of course, in a more complete detail, we include also indicating the depth of embedment of the footing. Okay, so I think that's all for this topic, no? Sa kuan.
Good afternoon, sir. Can I ask?
Sige, tayo mga questions?
How do you identify how wide the outer strip is, sir? Like, how do you identify how long is the outer strip and the middle strip?
Kabagay, kaya na iniagi nga motor sawa kayo.
Sir, can I ask, like, how do you identify the dimensions of the outer strip and the middle strip?
Well, the middle strip is the same. The width of the middle strip is the same as the short side of the footing, no? So if your short side is 3 meters, then you just place a 3 meter wide at the center, no? And the remaining distance will be outer strips, no? So 5.5
okay.
minus 3, it's 2.5 divided by 2, so 1.25.
Okay. Thank you, sir. Understood.
So any other question regarding this calculation? So next meeting, I will be starting to give you some assignments, no? Workout problems. So you will have the minimum practice, no? Hands-on on this calculation. So kanang atong mga plates has to be handwritten, no? And try to make your drawings does not necessarily have to be scaled, but better scaled. Since you have the ruler or triangle or drawing instruments, no? I will be giving you the problem set starting next meeting, no? Since we still have time, I'd like to show you the provisions of the code, because we only mentioned this one, no? So for the various load combination, so far we have only dead and live combination, no? That we have considered in the previous 2 examples. But in actual design practice, there are more than that, no? So section 203 of the code gives us the required or the minimum required, no, load combinations to consider in design. It states here that buildings, towers, and other vertical structure and all portions thereof shall be designed to resist the load combination specified in this section. So you have here the symbols annotation. So D is for dead, then E, earthquake, EM, estimated maximum earthquake force. You are referred to this section here. Then F, that is for fluid, H for lateral pressure, L for live load, then LR for roof live load, then P, that is the ponding load, then R is rain load, and T is for self-restraining force, for example, due to temperature, shrinkage, moisture, creep, no? And W is the load due to wind. Now, there are two sets of load combination. So the first set is on the load resistance factor design method, LRFD, or the strength method, no, which is the one that we are using in our discussion. No, we are using the strength design method for reinforced concrete and the load resistance factor design method for structural steel. So these are the load combination. So you have dead plus fluid pressure multiplied by 1.4, then you have 1.2 dead, then 1.6 live, no? This is the one that we should use in our load combination, no? We don't have fluid and self-restraining forces and no lateral forces, no? So kini siya, no, nasa kay combination of dead, live, roof live. Yeah, what is R here? R is rain load, no? Okay, so you have also combination of dead, wind, and edge. So these are some of the basic combination which you can see in the code, no? So load combination using allowable stress or allowable strength design. So you have here your load combination. But we are not using this since the design philosophy, in designing the reinforced concrete member is this one, and strength design rather than the allowable stress or allowable strength design. Alternate basic load combination. So, yun siya, So, pananglitan, since we are designing the size of the footing under service load condition, then for proportioning the footing, we should use this load combination. No load factor yet. Okay? So, dead plus live, mara mo na itong mga loads, So, atong i-consider. So, yun na, And, okay, other loads. I'm not going to discuss every item here, but I'd just like to show you that these things are in the NSCP, So for dead loads, that is the weight of the or densities of materials you are given here, Nasa code, panalitan masonry, how heavy is it, So that is 22 kilonewton per cubic. Okay? So naadiri ang mga material densities. Then for this in terms of pressure, that is kilonewton per square meter. So for ceiling, so depending on the type of ceiling, so these are the intensity of pressure which you can assume. So coverings for roof and wall, you have also here, depends on the type of cover. Then for floor and floor finishes, depende sad na adere ang mga ining recommended niya nga value. Now we have to exercise ining care, in not simply adapting blindly these values here. We have to check whether this one is consistent with the actual mga loading condition for certain projects. For example, might be different. For example, the required at the roof deck level, some would require a thicker concrete topping, So you just multiply the unit weight of concrete by the thickness of the concrete topping instead of simply using kanidiri nga mga values, Because there are certain assumptions here. I think for the concrete topping or cement finish, it is assumed 2 inches na siguro, Pero sa mga roof deck, usay mo require of 4 inches. Okay? Okay, floor live loads, you have also the table here depending on the occupancy. So table 205-1, so naadiri ang sa category, parking man na siya or ano siya, nakalista diri. hospital, libraries, if library, so what's the part of the library? Is it reading area? Is it stock area? Is it corridors? So you have your corresponding recommended mga pressure in kilopascals. Okay, so aside from the uniform load, you also have to consider concentrated load in some instances. So for example, for parking garage and ramps, so kanidire na ay subscript number 7. I think that will depend on the type of vehicle that will be parked in a certain garage. So office, nakakay in residential, sa residential, so basic floor area, exterior balconies, deck, storage. So you have their corresponding values, Panisya continuation sa table. Then here you have for roof live load, So there is a distribution. It mentions here how we distribute the loads. Then reduction of live load. If the load is applied over a large area, you can reduce the live load, So that is based on the statistical principle that a larger area is less likely to be filled up compared to a smaller area, At least most of the time. Now, this one, so minimum roof live load, so it depends on the roof slope. And there are two methods presented, Method 1 and Method 2. So just try to study this from the NSCP, You have to be familiar with the load calculation. It's very important, because if you got the wrong loads, then of course you will get the wrong design. So foundation investigation, so I think what is important here, for example, is the amount of boreholes, that the minimum required number of boreholes for a soil investigation. So it depends on the footprint area of the structure. If the area is less than 50 square meter, then you need only one borehole. If between 50 and 500, minimum of 2. If greater than 500, then you compute the number of boreholes based on this. So that's minimum of 2 plus for every 1,000, you have additional borehole, Okay, so what else? Okay, you have soil classification, questionable soils, then liquefaction studies. Very important, Then what do we have here? So expansive soil. So there is a requirement, on how we classify soil as expansive. So there are certain parameters here, Plasticity index of 15 or greater, then more than 10% soil particle past number 200 SIB. So it's very fine particle size. And more than 10% of soil particle less than 5 micrometers. Okay, so this is based on the SIB analysis, result. Expansion index greater than 20, determined in accordance with this standard, for testing materials. So recommended intervention of footing or foundation for building structure founded in expansive soil shall be designed in accordance with section, you have it here. And another solution is where the soil is removed, So you have soil replacement, can be a solution also. Okay, so for ignoring a footing or foundation placed on or within the active zone of expansive soil shall be designed to resist differential volume changes and to prevent structural damage to the supported structure. So you have to estimate the amount of differential settlement, So foundation extending into or penetrating expansive soil shall be designed to prevent uplift of the supported structure. Okay, so these are some of the things that we need to take into consideration. So you have also slab on grounds, removal of expansive soil, then stabilization, in case the soil structure is unstable, no? So there are different stabilization techniques, but this is already on the field of geotechnical engineering, no? And you have also structures on compressible soil. Okay. Now, the geotechnical report would include the following information, no? So try to check. When you read the geotechnical report from the engineer, you have to verify whether the information contained therein is complete, no? Diri ang list sa mga minimum information kinahanglan, no? Okay, so you have here the recommended ng mga laboratory and field test, okay? So usually the geotechnical engineer, they have standard tests, but if you want to do specialized nga mga or additional testing, then you have to specify, no, in your instruction, because that will have impact on the cost, no. Now, in lieu of kaning geotechnical exploration, nasa yung mga diri, no, kanang allowable foundation and lateral pressure. But again, these values has to be used with caution, no, because these are just more or less nga mga values, no. Ang sakto gid sabi na for very important structure is that you have to conduct a soil investigation, no. But without that, no, mga residential buildings, no, so pwede ra nga one story or two story nga mga structure, light ra ang ilang mga loading, then you can just assume, no, the soil bearing capacity based on this table. Of course, you have to still get some soil samples and try to classify what is the type of material, no. And if you, after classification, you have here the recommended allowable foundation pressure. So this might be overly conservative, no, resulting into not so economical design of the footing. Okay, so what else do we have here? Okay, you have sectional footing, so minimum requirement for foundation. So this is the minimum dimension, no? Depending on the number of floors to be supported and the thickness of foundation wall. So you have here the width of the footing, the thickness of the footing, and the depth, no, below the undisturbed ground surface. So these are just guides, no. It's just to be always checked based on actual site condition, no, because for example, if you have depth below undisturbed ground surface only 450 and there are two floors supported, no, 450 might be too close to the surface still, no. Example, naa ka sa ining rice field, no, i-reclaim nga rice field, so kani siya dili ni siya sakto, no? Okay, so what else do we have? So you have also vibratory loads. Because in the long run, no, vibratory loads will cause soil to have settlement, no. So kinahanglan nga i-kuana. Another way will be to make the foundation heavy in order to minimize the vibration, no. Or you can use vibration isolation, no, for the equipment foundation or equipment nga support. Okay, so you have here some building clearance from ascending slope, from descending slope, no. So I think this figure here is self-explanatory, no. Pools, then foundation elevation. So there are a lot of things to be read, no. As I said, lang eh, no, I don't want to go into this in detail. So kani siya, following formula may be used in determining the depth of embedment required to resist lateral loads in case you're, for example, in high-rise building, no, you have their huge lateral forces developed during earthquake, then what's the minimum depth of embedment of the foundation, no? So, naadire yung mga empirical formulas which are given. And some provisions on backfill and grillage foundation, shear footings. Okay, here we have the determination of allowable loads. I think this is on piles, no? So, of course, you have the pile formula, which is already beyond the scope of the subject. Static load test for determining the actual pile capacity. Then you can also have the dynamic load test, no, for determining the pile capacity. So commonly nowadays they are using dynamic load test because static load test requires a very heavy setup, no, itong testing equipment. But the static load test is of course more reliable, no? And the dynamic load test where the weight is dropped on top of the pile, then it makes use of the principle of conservation of energy. But again, the static load test simulates better the actual loading condition, no? Okay, so what do we have here? This is already in piles, so okay, let's try to see what's here. Foundation and geotechnical investigation. So where structure is determined to be in seismic zone 4. So in the Philippines, most of the country is within seismic zone 4. Only the portions in Palawan, no, are in seismic zone 2. So Cebu City, we are under zone 4, no? So this applies to most areas in the Philippines, no? So seismic zone 4 investigation shall be conducted and shall include an evaluation of the following potential hazards resulting from earthquake, motions, slope stability, liquefaction and surface rupture due to faulting or lateral spreading. So these are some of the things that we need to consider, no? So a determination of lateral pressure on basement and retaining wall due to earthquake motion is especially for multi-level basements, no, where the lateral pressure can be very high. So assessment of potential consequences of any liquefaction and soil strength loss. So I hope you read this through, no, so that you will be aware of the things you need to consider, no, in foundation design. So you have the for pier and pile foundation. So foundation construction, seismic zone 4. I think this is the one that we have already read this. Okay, so that's it. So I hope that you have a copy of the NSCP, because in our discussion we'll be quoting some of them. No, that's important. Important for you to be able to read directly, no, from the code. There are a lot of information there. Oops. Okay, so any questions so far?
Excuse me, sir.
Sige, Joshua.
I have a question, sir, but it's not regarding the topic you discussed earlier. It's about sa research, sir.
Oh, pero unsa man na pa yung mga question regarding sa subject matter na to karon before we entertain other questions?
Kan sir, asking ko sir, wala pa man to na-upload ang rectangular footing na PDF sir, no?
Upload naman siguro. We check ha.
Ay, di ko sure, pero pa ko nakita sir. Ambot sa others sir.
Ay, pasing pa dahil siguro ni.
Sir, no good question, sir.
Oh, nag-sync pa dire. So, kasi okay na siguro na. Just try to see, no? Kung naano ba dito, kay bago na ako na sync.
No, sir. Thank you.
Synchronize. Okay, so questions?
Sir, no good question.
Taman.
About sa footing, sir ba? When do you consider adding middle strips for the shorter side?
Ano sa mo consider og adding sa middle strip?
Yes, sir. Pananglitan ay mohang shorter side kay taas na sad.
No, ang sa rectangular footing, sa long direction steel, they are distributed evenly, no? But for the short direction steel, mo to siya ang distribution niya. Nakakay middle strip, niya nakakay outer strips. So sa long direction, always distributed evenly, no?
Okay, sir. So, no matter unsa kadako ang dimension sa
Oh,
footing, sir. Okay, sir.
in fact, sa square footing, the reinforcement are always distributed evenly, no, in both directions.
Sige, sir. Thank you.
Well, it might occur, no, in very rare situations where you have a very large footing, no. Panglitan, let me see. I'll share again my screen. Panglitan na kay column dire, no? And assuming that the bearing capacity is really small, or you have a very huge footing in relative to your column, no? So it might be medyo, I don't know if the footing is thin, no? Because kung baga ang atong footing, no, it will behave more as a rigid foundation, and I think even distribution of the reinforcement is okay, no. But for relatively thin footing, so you have to consider the footing and soil interaction, no. So dako kay imong footing nya nipis, of course the bending moment will be larger near the column when compared to the strips farther from the column, no? So pag maingon pa nga mo ni siyang atong critical section dire, but the distribution of the bending moment will not be uniform, no? So mas concentrated ang bending moment diri sa tunga dapit, mas gamay na lang diri sa ilid, no? Sa edges. So you might consider putting or even ang distribution sa load, no? Pwede ka consider a certain kind of pwedeng middle strip, no? Sa kanang direction, then also another middle strip in the opposite direction, no? But how wide this middle strip is, kung square footing ni siya, no? So pila may assume width sa middle strip. Well, that can be determined, no? There is actually no formula given in this instance, but you can do a more elaborate analysis. So for example, a finite element model will disclose, no, kay generate man ng software o stress contour or moment contour, no? And you can color code them, so the higher moment values will be color coded in red, whereas lower values will be in blue, no? So makita nimo asa gyud napita ang concentration sa bending moment, so ngadto sa nimo ibutang ang mas daghan nga steel reinforcement, no? So naay sitwasyon ngayon na pananglitan kini siya nga dako kay imong footing, no? And it is not so thick. So it will behave more as of a flexible footing rather than a rigid footing. So mga assumptions nga atong kining atong calculation is based on the assumption of a rigid foundation, no? That is why we didn't consider anymore the footing soil interaction. Okay. Okay, so what else? Nabaway laing question?
Sir, pwede ko mag-ask, sir, regarding lang sa katubi tong mga development lands and also kato mga dowel.
Murag hina ang imong audio?
Regarding sa katubi tong mga development lands, sir.
Oh.
Itong, di ba, naka-sir last time nga, i-check na to siya sa NSCP kay basi nagbago na tong mga coefficients.
Nya?
Okay, sir, makabalo may unsa siya nga section, balag ka ng kuan sa NSCP 2015, sir.
Okay, I'll try to scan it, then present it maybe next meeting, no?
Sige, sir. Thank you, sir.
Copy of the NCP is at the office.
Sige, sir. Thank you, sir.
Okay? So, sa pa?
Sir, ang next meeting ka next week na, sir, no? Kaya holiday man karon Thursday.
O mo ba? Sa holiday?
Osmania Day.
Apil pa dahil tanan ng mga holiday nga anong tayo adto-adto eskwelahan?
Basta na, sir.
I-declare ba nga no class?
Naay ning gawas na meron.
Na may ni-post sa Facebook, sir, good nga ni-declare ng university.
Wala siguro ta. Mag-klase lang ta, make-up class ta kay nawahin na ra ba ta? No? Umingit lang ta. Kailan naka-meeting sa atong na kuhan? Wa. Kira, mag-meet lang ta. Para maka-recover ta sa mga una nga mga kuhan, no? Wala yung taka-start sa class on time.
Understood, sir.
Anyway, di man yagi na rin motor nga saba kayo. Anyway, di man sa tanan siguro dito taga Cebu, di ba? Naman diri Aras probinsya. So dili apektado sa holiday, Mactan. Wala tayo po ay apil sa kuan. Di mo pa rin atong face-to-face nga naagi ta diri sa Cebu City tanan. No? Apektado tanan. Okay, so mag-meet lang ta karong Thursday. So any other concern? Okay, so na ako'y meeting pagka 3:30. So katong una po mo ilang concern, you still have time, no? At mga 25 minutes siguro. Sige. Arita sa mga other matters.
Unclear. I sent an email to you last September 3, sir. Nya katong you suggested a topic to our group, sir. Katong a comparative study of the various wall systems used in residential condominium buildings.
Oh.
ma-ask lang me regarding the topic, sir. Like, how do we kanang obtain data? Like, mag-search mig kanang mangita or mig condominium, a specific condominium to conduct our study on.
Well, kuan usa pwede mo magsugod og research sa internet, no? Daghang mga products karon sa mga wall systems. Na fortress, na light blocks, na light strong, na photo AEC panels, na mga sandwich panels. So there are different nga kuan, no? You can ask tingali mga contractors or developers unsa nga mga system ang gigamit nila, no? Just a survey of the kuan, no? Of course, ang pinaka basic na ang concrete hollow blocks, no? Pero na may mga wall system karon nga paspas gi-install. So maybe you can focus on interior wall systems, no? And
Sige, sir. Yeah. Regarding sa the answer, like, kanang sa pagka-advisor, sir, would you be willing, mas prefer nimo if like co-advisor ka, sir?
okay ra.
Okay, sir.
Co-advisor lang.
Okay, sir. Ako lang i-resend balik ang katong notice of, I'll send it to your email, sir.
Sige.
Okay. Sige, thank you, sir. And regarding sa the budget for the research, sir, kay di man mo come out as okay, sir. I delayed this, sir, never mind. Mag-send na lang ako balik sa email, sir, sa notice of acceptance. Sige. Thank you, sir.
Okay.
Excuse me, sir. Good afternoon.
Sige, naman.
Naaking gi-email sa imo hapon, sir. Pwede nimo i-check later?
Unsa man nga kuan?
Ay, about sa amo ang topic, sir ba?
Unsa man nga mga tubos nga topic? Unsa inyong gi-propose nga topic?